integration by parts is undoing the product rule. So we're going to review our product rule, look at how it might work, develop a formula, which is the formula for integration by parts, and then see how we can use it to solve some of the ones that I gave to one of the groups yesterday and how it can be used. So first of all, you would look at an integral and you would still try to do all of your integration rules that you know so far. So if you can do your standard integration rules, perfect. If you see substitution, which you start looking for a function inside of another function where its derivative or a form of its derivative is present, then you're going to want to use substitution. But when both of those things don't happen, another way of integrating is integration by parts. So here's a little review of our product rule. Okay, and this notation says if I have two things multiplied together and I want to take the derivative, I keep one the same, derivative of the other one, then I keep the other one the same, derivative of the first one. Product rule, we've done a fair bit already. Now what we do with that product rule is we now say, what would happen if I integrated both sides? So if I integrated the left side of my equation and integrated the right-hand side of my equation, we know that integration and derivatives undo each other. They're opposite things. If you take the derivative and then you integrate, you get back to what you started with. So on the left-hand side of the equation, if I'm doing the integral of the derivative, I'll just get back what I started with. So I write that as f times g. Those are the two functions multiplied together. And on the right-hand side, we have an integral rule that says if you're adding two things and you're integrating, you can integrate each one separately. So what we have after taking the product rule and applying integration to both sides is we have this line right here, that the original function is equal to the integral of this plus the integral of that. If we rearrange this to get the integral of fg prime by itself, can you see that I can do that just by subtracting that to the other side? Now, this notation isn't sort of like, you could use this notation, but we're going to simplify our notation similar to what we did in substitution. So there's sort of an element of the ideas of substitution in integration by parts. So what does that look like? We let u equal f of x and v equal g of x. So our original two functions that we're multiplying together, f and g, we make one of them u, one of them v. Then if you took the derivative of u, du, so we're sort of going into Leibniz notation, is equal to f prime of x dx. And dv would be g prime of x dx. So we're moving that dx over just like we did with substitution. And we can now change this equation that we rearranged. Instead of f, we can write u. And instead of g prime dx, we can just write dv. And what that does is just cleans things up a little bit. It makes less things happening inside. We still have f and g, it just becomes u and v, so that part doesn't really simplify. But here too, instead of g f prime dx, we have just v du. So it's a little bit cleaner, and the idea is if we can take our original integral. So this is what on the right-hand side is the original one that we do not know how to do. And we make a substitution. We decide we're going to make something u and we're going to make something else dv. If we do that, we hopefully can work backwards from whatever we decided dv was to find v. And we can take the derivative, that's always easy, to find du. And hopefully what appears in here is something that we can do with our standard integrals or with integration that we know up till now. That's the plan. We take an integral in the green box on the left that we can't do. We say, I'm going to call part of it u, I'm going to call another part of it dv. I can then find v and du and write the right-hand side and hope, because sometimes it does not work, but hope that what I write on the right-hand side is something that I can find the integral of. So let's look at a first example. And up here at the top, we'll rewrite integration by parts rule. So what we're trying to figure out here, we have to, that would be the left-hand side of our formula. We have to decide something to be u and something to be dv. Well, I see a product of two things here. So I could either let u equal x and dv be the e to the 3x, or I could let u equal e to the 3x and the dv equal to the x. If you try one of them and it goes nowhere, the suggestion would be to try the other one. Okay? Now, as human nature would go, so will I. Human nature would say, oh, since the formula says u and dv, I'm going to make u my first one and dv my second one. Try that first. And in this case, it will be the right way. So we let u equal x, and dv would equal e to the 3x dx. First of all, can you see that I have covered everything then inside of the function with that substitution? Then we could take the derivative of this one. What's the derivative of x? Would just be 1. Are you okay if I write du equals dx? On the right-hand side, if I wanted to find v, I would have to integrate, work backwards from dv. How do I integrate e to the 3x? Well, it would be the same, but I'd have a chain rule where I'd have to multiply, so integrating, I'd have to divide. And although there should be a plus c right now, we don't write it, because in the end we'll have a plus c, and all of the little plus c's that happen in every single part will get combined, because there's just going to be a constant at the end. So we do not need to write it here. We can just write this at this point. We now apply the formula. So what we have is supposed to be equal to u times v minus v du. So we have equals u times v, x times e to the 3x divided by 3 minus the integral of v e to the 3x over 3 times du, which is just dx. And our hope is what we put in that second integral is now something we can integrate using our normal integral rules. And we can. It's just an e to the 3x now. No extra baggage. How do we zoom page width? And so here we'll get 1/3 x times e to the 3x minus, and this integral would be e to the 3x divided by 3, but you have another chain rule that you'd have to divide out, divide by another 3, and here you can add the 1c that represents all constants added in the end. And so our final answer, if we wanted to simplify this, is 1/3 x e to the 3x minus e to the 3x divided by 9. Just for fun, check. Let's say this is equal to y. Check by finding the derivative. If we are right, our derivative should match what's inside of this originally. Because if we integrated and got an answer, we should be able to do the derivative and get back to where we started from. Can you see that we have a product rule in the first part? Product rule says keep the first one the same, derivative of the second one. And how do I do the derivative of e to the 3x? It stays the same. Then a chain rule, which means multiply by 3. This is where you have to be paying lots of attention, because sometimes you're doing the chain rule for integration, you have to divide, and sometimes you're doing chain rule for derivatives and you have to multiply. So easy to mix them up, because you're going to be worrying about what you have to do next, so you might not be concentrating on what you're doing right now, which is a common human trait across all things. Most people get into the most car accidents the nearest their home because they've driven it so many times they no longer have to think, which causes them not to think and get into more accidents. Maybe. So here we go. Product rule. Keep one the same, derivative of the second, plus keep the second one the same, derivative of the first. And then we'd have minus derivative of this one which is another chain rule multiplied by 3. I'm just going to simplify a little bit. Can you see the 3 and the 1/3 will simplify? That will just give me x e to the 3x. This is going to be 1/3 e to the 3x. The 3 and the 9 here will be 1/3 as well, and you're subtracting them. Can you see that these two are identical and they'll equal 0? So we now have our simplified version. Is that what was originally in our integral? Yes. So we know that we were right in calculating our integral here. Crazy. And not too bad. So now that we've done one example, I want to go back to thinking about the product rule, because thinking about this is going to be key for helping you remember the formula. So we've got our product rule, which you guys all have memorized already. Keep one the same, derivative of the other one, keep the other one the same, derivative of the first. When we integrate both sides, okay, we have the idea that integral of a derivative, that just cancels each other out. And then we can integrate each part separately. We rearrange this to get one of these by itself. U dv is the one that's generally put by itself. With that in mind, the simple substitution makes this become the integral of one derivative of the other equals both of them minus the integral of the other one derivative of the first. See how it's so much like the product rule, just rearranged. I mean, you could bring the uv to this side, or bring this one to this side, and you really have the product rule just rearranged. Okay? And so the reason we write it this way with, the reason I like to write it this way is with the u comes before v, so you have like, okay, there's u and then dv as the next thing, just alphabetical order can help out here. Then the process is we have to make a decision what we're going to make the u and what we're going to make the dv. This may or may not work on your first try. You might choose the wrong ones. Some of the mental process that I looked at when I do this is I think whatever I make u and dv, I want v and du to be something simpler. So in this case, by making u the x, my du just becomes dx. It gets rid of that x in the front, which was sort of the problem to begin with. And then when I plug it into the formula, now I just have one of those functions present instead of both of them. All right, let's do another example. 2x cos 5x. First of all, we're multiplying, so that should get rid of any kind of regular integration rules that you would think. I'm going to try to pretend this was mixed in a bunch of integration ones, so you have to think about all of your rules, instead of it being the second question in your integration by parts notes, which seems to imply that this will be integration by parts, which it is. Right? But you have to sometimes say, contextually, if I didn't know it was integration by parts, how would I get to that point to say this is going to be integration by parts? So first, I see multiplying of two functions. That's going to throw out your basic integration rules. Secondly, I would go to substitution. Substitution is when you see a function inside of another function and its derivative present. Here, I see a 5x inside of cos, but the derivative of 5x is not 2x. So I have a problem with substitution, which then says, I guess I have to try integration by parts. So I need to make u equal to something and dv equal to the other part. And again, you have choice here. You could have made the u the cos 5x and the dv the 2x. In this case, I thought, I like to make u the 2x because when I do the derivative of 2x, I just get 2. So it looks like I'm going to have a simpler integral later. Can I work backwards from cos 5x? Integrating cos, will it be positive sign or negative sign? I haven't put the sign out in front. Should it be a plus sign out in front or a negative sign? Derivative of sine is positive cos. So the integral of cos would be positive sine. Good. And now we can go to our formula. I'll write out the whole thing. If I had the integral of 2x cos 5x dx, I made this u would be 2x times by sine 5x over 5 minus the new integral of v sine 5x over 5 du, which is 2 dx. So once we've decided on our u and dv, and we figured out our du and our v, we just write out the formula, and this is where we're very hopeful. We're hopeful that the new integral on the right-hand side is something we can do. So I'm just going to rewrite this first one as 2/5 x sine of 5x minus, And there, can I integrate that? Working backwards from sine, you would get cos, positive or negative. I'm going to write the 2/5 out in front. That's there. As working backwards would be negative. It's going to be negative cos 5x. Can you see you would have had a chain rule? And when integrating, you would have to get rid of that chain rule, so we need to divide by 5. And we can add our plus c now. So simplifying this out, we're going to get 2/5 x sine 5x, negative, negative, plus 2 cos 5x all over 25 plus c. And what's amazing about the answer, in my opinion, is it would take me a long time to guess and check to think that that's what I should have done. Okay? So notice that integration by parts, your answer always has, as far as checking with the derivative, you would always have a product rule, and then there's always something sort of that compensates for something in the product rule that no longer appeared. So if I would do the product rule, I would get a negative 2 cos 5x over 25, which I now have to add 2 cos 5x over 25 to get rid of. Another one that I gave you guys yesterday to try, the integral of the natural log of x. One group was working on this, and they were stuck. And then I said, hey, try this derivative. And if they knew which derivative to try first, they could figure it out. But now we're going to say, how can we use integration by parts to figure this out? Can you see that initially when you look at this, there's no product? And yet, this isn't one of our derivatives that we know that we can do just a standard integration rule. Initially, you would go, oh, this looks like a standard one. And then you're like, I don't know any derivative. That's just the natural log of x. Obviously, there's no substitution because I see only one thing, and I don't see a derivative, and I don't see a function inside of a function. Okay? So can I purposely do it wrong first? Okay? I'm going to say, I'm going to try integration by parts. I could say, ooh, there is a number out in front. I'm going to make u equal to 1 and dv equal to the natural log of x dx. Okay? This is easy. du is equal to 0. This, if I want to find v, I have the same problem that I started with. Do you see that? That in order to find v, you'd have to integrate the natural log of x, and that was the original question. So we could do integration by parts again and use the same substitution that we just did and do this loop infinitely until we die. Not recommended. So we realized this is not going to work. So we say, well, what happens if I made the u the natural log of x, and then dv just the 1 dx? I've still covered everything inside that integral. But now this is an integral I know how to do. I mean, that's a derivative I know how to do. And I can integrate here. in order to get 1, v would have had to have been x. So using our formula, u times v, x times ln x, minus the integral of v times du and it works out beautifully. Because this, so we just have x ln x. This is 1. The integral of 1 will be minus x. And of course, we remember to do plus c. And you found that yesterday because I got you to do the derivative of x times ln x. And from that derivative, you were like, ooh, we just need to get rid of this extra x. Why don't we subtract x to get rid of it? And it works. But now you can see that the integration by parts, just rearranging our product rule, allows us a method to figure it out. Especially when, like, how long would it take me to guess and check to find out that that was right? Okay, normally I get you to do one by yourself now, but this one has additional problems. Because you know how in the chain rule, sometimes you had a chain rule inside of a chain rule, inside of a chain rule, inside of a chain rule. Sometimes you have integration by parts inside of integration by parts inside of integration by parts, and so on and so on and so on. That's what's going to happen here. But I've made it a little bit simpler. So again, we decide on something for u, something for dv. Integrate, so du to x dx. Oh, sorry, I used the wrong word. Take the derivative. Differentiate would be the right word. Differentiate here to get du. Integrate here to get v. Going backwards from sine will be negative cos. Divide by 5 because there would have been a chain rule. Write out our integration by parts formula. Our original function will equal u times v, x squared times negative cos 5x over 5, minus the integral of v times du. The integral that we got has a 2x and a cos 5x in it. But it's still one that cannot be done using our normal rules. However, as Ethan's flipping his page around, it sure looks a lot similar to one we already did. Which one did we do earlier? Go back. We did 2x cos 5x earlier. So I'm going to cheat a little bit. I'm going to go equals. I'm going to write this as negative 1/5 x squared cos 5x minus, I'm going to bring out the negative and the 5. So I'm going to make it plus 1/5 integral of 2x cos 5x dx. Maybe you take out a different color pen. and tell yourself you're going to cheat a little bit here and copy the answer you got from B, because we figured out the integral of 2x cos 5x using integration by parts in part B. And so we would get negative 1/5 x squared cos 5x plus 1/5 bracket, and I'm going to copy out my answer from B, which was 2/5 x sine 5x minus 2/5 plus 2 over 25 cos 5x. And we'll just put our plus c at the very end. So our final answer is negative 1/5 x squared cos 5x plus 2/25 x sine 5x plus, distribute the 1/5, 2 over 125 cos 5x plus c. Whew. And you could check if you wanted to if this was right by taking the derivative. But can you see you have two product rules now? You have a product rule in the first term and a product rule in the second term. And then you have a whole bunch of like things to combine to find out if this works. All right. I'm going to get you to try this one. I'm going to let u equals x and dv equal, and I'm going to change that square root to a half right away, x plus 1 to the half. One thing I like about making the u equal to x is when I do the derivative of that, it becomes simpler. So it's telling me my formula, I'm going to get things to be simpler. Here on this side, at first I was a little timid about making this one x plus 1 to the 1/2 because it seemed like the more difficult integral to do. But integrating this is just add 1 to the exponent, divide by our exponent. And so now we can say that our original integral will equal u times v, so x times, and I'm going to multiply by the reciprocal, so I get a 2/3, minus the integral of v. So again, I'll have that 2/3 out in front, times du, and du is just dx. And so what's inside my integral is now almost identical to what my dv was originally. And bring that 2/3 out in front of everything, minus, add 1 to the exponent again, so now I'm going to get 5 over 2 and divide by 5 over 2 plus c. Multiply by the reciprocal. And we're done. Beautiful. So again, the idea is with integration by parts, we make a new integral, and we hope that that new integral is something that's easier to integrate than what we started with. If it is, life is easy. Life is good. I'm going to show you, though, just for fun, a substitution for this one. So using our substitution methods. Now, this one doesn't match up with normal substitution methods in that I do see a function inside of another function. I see x plus 1 inside the square root. But the derivative of x plus 1 isn't x. So at first, it appears that substitution shouldn't work. Because if I let u equal to x plus 1, then du is equal to dx. And as far as substitution goes, where's their problem? I still have an x out in front. However, a little bit of creativity says, if u is equal to x plus 1, would you agree that x is equal to u minus 1? And if I do that, I have three things I can now substitute into my formula. My integral becomes, instead of x, I can write u minus 1. Instead of square root of x plus 1, I can write the square root of u. Are you okay if I change that to u to the 1/2 right away? And instead of dx, I can write du. Here, I can distribute. Before with the x's, I couldn't. And so, I get u to the 3/2 minus u to the 1/2 du, and that is a simple integral, your basic integration rules. So add 1 to the exponent, divide by your new exponent, which I'm going to multiply by the reciprocal right away. Add 1 to my exponent. We would divide by 3/2, but multiplying by the reciprocal right away, 2/3 plus c. And then we can substitute back in what our original And again, the answer doesn't look the same as the other answer, but it is correct as well. Whew. But that is a really neat substitution because there's sort of like an extra substitution that happens within. And then you're allowed to distribute and your integration becomes easy. Yes? Oh. And then you could multiply it. So what he's saying is he was doing the same thing, but here, multiply both sides by x. But then you would get, when you substitute it in, you would still get an x.
Yeah, still substitute u minus 1 for that.
Oh, then you did u minus 1 after that. Okay. Okay. Perfect. Excellent. Okay, so in your textbook, we're going to go up in the last 20 minutes. We're going to do these ones on question number 1 in our groups up on the boards for the last 20 minutes and practice some of these integration by parts. Oh, by the way, the on is grammatically incorrect when it's on that angle.